A new day has just begun. You wake up, take your morning shower, make your coffee, answer a few messages from your friends and your dad. You take a sip of the coffee that's gone slightly cold, as usual, but you don't really mind. Everything feels completely normal. But none of it ever happened. In fact, nothing you've ever experienced happened. This video is about an idea that follows from one of the most fundamental concepts in physics. An idea that, under the right assumptions, suggests what I just described may actually be more probable than the reality you think you've experienced. To understand why, we first have to talk about entropy. Entropy is often described as a measure of disorder. The second law of thermodynamics tells us that natural and spontaneous processes always result in an increase in the total entropy of the universe. That cup of coffee from this morning followed exactly that principle. As it sat on the table, it slowly transferred heat into the colder air around it until both became slightly closer to the same temperature. The thermal energy started out concentrated in one small cup before gradually spreading throughout the surrounding air. The system appears to go from something ordered to something more disordered. In other words, from low entropy to high entropy. Instinctively, you'd think that the temperature difference itself is what drives the process. That heat simply wants to flow from hot objects to cold ones. But that's not the whole story. The temperature difference tells us how heat flows, but it doesn't explain why. And while disorder is a useful way of thinking about entropy, it's not really what entropy measures. It's about probabilities. Physics contains different kinds of laws. Some laws describe what must happen, others describe what is overwhelmingly likely to happen. If you're standing on Earth holding a rock, and you let go, it falls every time. We don't usually think of gravity in terms of probability, but entropy is different. When your coffee cools down, physics isn't saying that it had to happen. It's saying that out of all the possible ways the particles in the coffee and the air could be arranged, an even distribution of energy is so overwhelmingly more likely that it's the outcome we would almost always observe. The important word there is almost. If almost always still leaves room for exceptions, what do those exceptions actually look like? If you shuffle a deck of cards, you'll almost certainly end up with a random order. But there's nothing stopping the deck from ending up perfectly sorted. It's just unimaginably unlikely. The same is true for your coffee. There's nothing in the laws of physics preventing all of the thermal energy from randomly concentrating back into the cup. It's just so unlikely that, for all practical purposes, it never happens. But never and impossible are very different things. Physicists call these incredibly rare events statistical fluctuations. Fluctuations happen all the time. Most of them are so small that we never notice them. A few more molecules drifting to one side of a room than the other. A tiny concentration of energy appearing somewhere for a fraction of a second. Events like these are happening constantly, but the larger the fluctuation, the less likely it becomes. A fluctuation involving a few molecules is relatively common. A fluctuation large enough to noticeably warm your coffee is unimaginably less likely. In fact, the probability of that happening is approximately 1 in 10 to the power of 10 to the power of 20. That's 1 followed by 1 quintillion zeros, a number so large that writing it down would require far more digits than there are atoms in the observable universe. It's possible, but unlikely enough to confidently say that it will never happen. But here's where time comes in. Some cosmological models predict that the universe could exist for unimaginably long periods of time. If the probability of an event is greater than 0, then given enough time, even the rarest events can eventually occur. There could be fluctuations large enough to warm your coffee, large enough to assemble a planet, large enough to create an entire human being, from nothing more than randomly arranged particles. And this brings up an even more interesting question. If probability always favors the smallest possible fluctuation, why would a statistical fluctuation recreate an entire universe with billions of years of cosmic and biological history just to produce a single observer? Why not simply create the smallest fluctuation capable of becoming one? Think about everything that had to happen for you to exist. The universe had to begin in an extraordinarily low entropy state. Matter had to form, stars had to ignite, heavy elements had to be forged inside those stars before being scattered across space. A solar system had to form around one particular star. A planet had to end up at just the right distance. Life had to emerge. Evolution had to unfold over billions of years. Eventually, after countless generations, you were born. That's an astonishing amount of history. But now ask yourself something different. How much of that history is actually required for you to remember it? If a statistical fluctuation were somehow able to create a brain identical to yours, with the exact same neural connections, same memories, same personality, and the same sensation of sitting here, watching this video, would that brain know the difference? From its perspective, it really did wake up this morning, take a shower, make a cup of coffee, and text its friends and family, with whom it shares years of memories. And those memories would feel just as real as yours does now. But none of those events would actually have happened. They would simply be memories that came into existence along with the brain itself. A hypothetical observer like this is known as the Boltzmann brain. And if statistical fluctuations really do favor the smallest possible arrangement of matter capable of producing an observer, then in those cosmological models, creating a single brain with false memories is vastly more probable than recreating an entire universe with billions of years of cosmic history just to produce the exact same observer. But just because one scenario is vastly more probable than another doesn't mean that the other is ruled out. Now imagine a universe that exists long enough for both ordinary observers and Boltzmann brains to appear. If Boltzmann brains are vastly more probable, then over enough time, they would vastly outnumber ordinary observers. So if you were to randomly pick one observer from that universe, which kind of observer should you expect to be? Typicality says, statistically, that you should expect to be whatever kind of observer is most common. And that's where this stops being a thought experiment and becomes a problem for cosmology. A successful cosmological model shouldn't just explain how a universe evolves. It should also predict the kind of observers that are most likely to exist within it. If the model predicts that almost every observer should be a Boltzmann brain, while we observe a coherent universe with a consistent history, then many cosmologists see that as a sign that the model itself needs to be reconsidered. And that's an important distinction. The Boltzmann brain hypothesis isn't widely discussed because physicists think we're probably Boltzmann brains. It's discussed because it reveals something surprising about certain models of the universe. Science usually tells us what exists. The Boltzmann brain idea forces us to ask a different kind of question. Not what exists, but what we should expect to observe if the laws of physics and probability are taken seriously. Whether Boltzmann brains actually exist is almost beside the point. In fact, one reason the idea remains important is that many modern cosmological models are expected to avoid a universe dominated by Boltzmann brains altogether. The thought experiment survived not because physicists accepted its conclusion, but because they took its implications seriously. Maybe that's the strangest thing about science. Sometimes its most unsettling ideas don't come from breaking the laws of nature. They come from following them to their logical conclusion. The same statistical principle that cooled your morning coffee can, when followed far enough, challenge everything you think you know about your own past.